Welcome back to CS 111. In the previous lecture, we learned about double-ended queues or Deques, and we saw how we could implement one using linked nodes. In this lecture, we're going to take a look at a different approach using a circular style array to implement our Deque. Let's go ahead and start looking at what circular arrays are and how we can use them as we implement our Deques. With the different types of data structures we've looked at so far, when we've used an array for our implementation, we've had it set up so that the front or top of our data structure was stored beginning in element 0. If there was anything in the data structure, there was a value in element 0. That sort of approach has some shortcomings when we get to Deques, where we're able to add and remove items at both the front and at the rear. So let's say that we have two items, B and C, stored in our Deque right now, and we want to go and add another item at the front. One approach, the one that we would do with a traditional array, would be to go and shift over all the existing elements by one position to go and free up element 0 for the new item that we wanted to store. The thing is, this sort of approach requires a lot of work to go and move things around. Every time we add or remove anything at the front, we're having to go and shift positions. So there's a lot of movement operations that are required. When we use a circular array, rather than having element 0 always represent the front of our Deque or whatever data structure we're using, the front is going to actually float, and we'll have a field whose job is going to be to keep track of what element in our array represents the front. The array is called circular because we say that it goes and wraps around at the front and the rear. So if we're in element 0 and we want to go to the element before it, that element actually exists, and it's the last element in the array. So here, element A, which is our front, is stored in index 4. Index 0 is not the front, even though it's index 0. But basically we say that 0 comes after 4, and vice versa, with 4 coming before 0. So here, we're keeping track of our front index at A as being in element 4, and then we can go and keep track of the size as we've been doing, so we know where the rear is, basically as going through and doing the front, plus however many positions come after that. So our rear here is still going to be C. We'll just have some empty elements between the front and the rear. And what's going to happen here as we go and add and remove things from our Deque, the positions of the front and also the rear can go and shift over time. With this approach, all we have to do is keep track of which index represents the front of our data structure. We don't have to be continually going and moving the values around so that it's always element 0. This goes and saves us a lot of work and can help improve the performance of our circular array-based approach as opposed to a traditional approach. When we go and design our circular array Deque class, we're going to have 3 fields in it as opposed to the 2 that our other array-based implementations of different data structures have had. We're going to have a field to keep track of our data array. We'll have a field to keep track of the size, showing how many items we're actually using in our data array. And then we're going to have that extra field to keep track of which array index represents the front of our Deque. Let's go ahead into Eclipse and we'll see how we can go and code up this approach. While it does have some pretty nice performance characteristics that allow it to work a little bit better than a traditional array-based approach, some aspects of the implementation are going to be much more complicated. So we'll see how those work, and you can kind of evaluate for yourself if you think it's a worthwhile trade-off. Here in Eclipse, I have the deck interface project from the starter code for this lecture. I also went ahead and created a circular array deck project, and I added deck interface to the Java build path for my new project. Let's go ahead and create a package in our new project to store our circular array deck class. In keeping with the naming convention that we've been using, I'm going to go and name my package as edu.wvu.cs111.circularArrayDeck. And then inside of there, I'm going to go ahead and make a new class that I'm going to call circularArrayDeck. And I'm going to list that it goes and implements our deck interface. So under interfaces here, I'll go to add. I'm going to go through and start searching for deck interface if it's not already appearing there. And then we'll go and, once we've made sure it's listed here, click finish. Inside the new class, I'm going to add the tgeneric for our circular array deck class. I'm going to use the quick fix for Eclipse to go ahead and add the unimplemented methods. And then I'll provide some JavaDoc for my new class. Let's go ahead and take care of our fields now. I'm going to start off by creating a constant with the default capacity for the deck if we don't specify some other size when we go and create it. So this is going to be marked as public because constants are normally set to be public. It'll be a static and final, so we can't change its value once it's been set. And it's going to be an int. I'll call it default capacity, capitalizing the name and using underscores in place of spaces, as is the naming convention for a static variable like this that's being used as a constant. And I'm going to go and set the default capacity as 25. I'm also going to go ahead and create the 3 other fields that I need. I'm going to have a protected array of type T that I'll call data, and that's going to store our actual information. I'll have a protected int to keep track of the size with how many items we actually have stored in the deck. And then I'm going to have that additional protected int field to keep track of which array element index has the front of our deck. And then I'm going to go and provide some JavaDoc for these different fields. When we go and call the constructor for our new circular array deck class, what we're going to do is create a new array based off of whatever initial capacity we specify either as a parameter or the value that gets used from the default capacity if we don't specify an argument when we go and call the constructor. We're going to go ahead and store that array inside of the data field. We'll also want to make sure that we go and initialize both the size and front index fields to 0. Size is set to 0 because, at least initially, we don't have anything stored inside of our deck. Front index is set to 0 just because that will give us a reasonable starting place for things here. In theory, we could go and set this to any index that we wanted, but I think it's kind of cleanest personally just to start off at 0. So when we go and do our first add or insertion, whether it's at the front or at the rear, that it'll go and happen in element 0. As we've been doing with our other array-based implementations of data structures, we're going to provide 2 different versions of the constructor. One that has a parameter for the initial capacity, and another that doesn't and just uses the default value. Let's go ahead and code up the version of our constructor that has the parameter first. So it's going to be a public method called circularArrayDeck, and it's going to have this int for the initial capacity. Inside the body of the constructor, I'm going to create my new data array, and I'm going to store this in the field this.data. it's going to be a new array of objects because I can't directly make an array of a particular generic type. And the size is going to be initial capacity. And then I've got to go and make sure that I cast that array once it's created to be an array of type T. I'm going to go ahead and set size to indicate that we have an empty deck. So I'll set this.size equals 0. And then I'm also going to initialize the front index to 0 so that we go and start off with putting our first new item in that index. Now, size and front index, those are both going to be 0 by default just because that's the default value for a primitive int, but I like going through and including the code to set those just so that my intentions are clear. Not that I forgot about those fields, I specifically want them to be set to 0. I'm going to go ahead and have Eclipse go and add a suppress warnings annotation to this method here to go and get rid of this warning here about an unchecked cast. That cast, I'm not necessarily going to be able to make sure that it's actually safe, but it actually should be. And this way I don't have the warning displayed because, I know this is an issue. There's not really any way around it. And then I'll go ahead and provide Java doc for this version of the constructor. So we're going to create a new circular array-based deck with the specified initial capacity. And our initial capacity is going to be the initial capacity. For our second constructor, this one's not going to have any parameters. It's going to be public, and we'll call it a circular array deck to match the name of our class, but we'll have an empty set of parentheses. And what this constructor is going to do is, it's actually just going to go and call our other constructor to do its work. For the initial capacity parameter, we're just going to specify what's stored in our default capacity constant. So I'm going to call this, since that's the way we go and call the constructor for this current class, and I'm going to say that I want a circular array deck dot default capacity for the size. And we'll add some Java doc for this as well. So we're going to create a new circular array-based deck with the default initial capacity. We're going to have a number of helper methods to support the operation of our circular array. We're going to code up some of these here first because we'll be making use of them when we get into the methods that are required by our deck interface. The first of the helper methods that we're going to create here is going to calculate the array index that we want to access, and it's going to take into account wrapping around the front and rear of the array. I'm going to have this be a protected method, and it's going to return an int. I'm going to call it calculate array index, and it's going to take two parameters here. It's going to take an int with the starting index that I'm looking for, and then an int with the offset. So the starting index here is intended to be the actual array element that has, for example, the front of my deck or the rear of my deck, and then the offset is going to show how many positions I want to move relative to that. So if I want to go before it, I might say that I want to have an offset of -1. If I want to go into the array element after it, my offset would be +1. What we're going to do to start off our calculation here is to go and apply the offset to the index, and then we'll handle wraparound. So I'm going to create this new int that I'm going to call updated index, and that's going to be calculated by going and taking the original index and adding the offset or subtracting it if it's a negative offset. And then I'm going to do mod this.data.length. That mod part there is going to handle wrapping things around. So if I run out of elements at the end of my array, we'll just come back to the beginning. As an example, let's say that I have an array that is length is 5. It's got room for 5 elements. If I go and start off with an index of 2, and let's say that I have an offset of 4 for some reason here, like maybe I'm trying to go through and calculate where the rear of my deck is going to be. So I have 2 plus 4, go and mod that by 5, I'm going to end up with the updated index value being 1. So we've looped back around, we've wrapped around the array to the other end of it. We need to make sure that the index that we are going to return from this method is a number that's at least 0. Arrays always have an index of greater than or equal to 0. We don't have negative indexes in our array. Depending on the value that we're providing for the offset when we go and call this method, at least initially, the result of updated index could be a negative number. For example, if I have a starting index of 0 and I have an offset of -1, 0 plus -1 is -1. And this mod operation is not going to change that. I still have a negative number. What I want to do is go and take that -1 and translate it to a positive number that's going to go and correlate with the actual element that I'm trying to use. So what I'm going to do for that is I'm just going to go and add the size of my array to updated index however many times I need till I end up with updated index being greater than or equal to 0. Normally if I have to do this, it would only occur once, but I'm actually going to go and set this up so that even if somebody gave a really big negative offset that was several times the size of the array, my code would still work and return a 0 or positive index. So I'm going to say here, if my updated index is less than 0, then we're going to wrap around a positive. And we're going to do this by using a while loop. This is what's going to handle things so that it works correctly regardless of what offset is provided. So I'm going to say while updated index is less than 0, I'm going to go ahead and loop, and I'm going to go and add to updated index this .data.length. So that's going to go and add whatever size my array is to the updated index. So if I have an updated index that's initially -1 and I have an array that's of size 5, I'm going to end up with my new index being 4, which is the very last index in the array. And since we're saying things are circular, that would be the one that's before index 0. So that's the behavior that we're looking for. Once we've gone and ensured that we have a non-negative index, we're ready to go and return updated index. And then we'll provide some JavaDoc for our method. So we're going to calculate the array index after applying offset and wraparounds. So our index is going to be the original index, or basically our starting point. Our offset is the offset to apply, and I'm going to note that this could be positive or negative. And then we're going to return the index with offset applied. Our next helper method is also going to be marked protected and return an int. And this one is going to calculate which element index in our data array corresponds with the rear of our deck. So we don't have a separate field where we're keeping track of the rear position. We just have one where the front is, and we know what the size of our deck is. So I can go through and take front index and the size and go and figure out from those where the rear is without me having to have a separate field that I have to remember to keep updated. This calculate rear index method's actually going to rely on calculate array index to go and do its work. So what we're going to do is return the value we get from calling that other method. And for the starting point index that we're going to go and provide, that's going to be this .front index. And then our offset is going to be the size that we have -1. And I'm going to add a comment here that I'm doing the offset as size -1 to avoid overcounting the front element. So let's say that I have a deck where the front index is 0 and I only have one thing in the deck. So that means that my front is also my rear. So both front and rear should be 0. If I went through and just had this dot size, it would go and say that my rear was 1, when in fact index 1 is actually the spot after the correct rear index here. So I'm going through and doing the -1 on the size just to go and account for the fact that we actually are storing things inside of front index. I'm going to go ahead and provide some JavaDoc for this method too. So this is going to calculate the data array index of rear item. And we're going to return the index of the rear item. Let's also go and take care of our isEmpty method right now. And for this one here, we're just going to return if the size is 0. It's going to return the result from evaluating the expression this.size equal to 0. Next, let's go ahead and take a look at the methods for peeking at the front and rear items in our deck. Remember that when we go and peek, we return the value that's stored, but we don't actually remove it from our deck. We'll start off by looking at peeking at the front item. We're going to have to make sure, first of all, that there are values stored inside of our deck. If there aren't, we're going to throw a no such element exception. And the reason why we're doing this is so that we're able to safely store null values inside of the deck if we choose to. If I allowed nulls and didn't throw an exception with this method, I would run into problems with distinguishing between a null that might get returned because there was nothing in the deck versus a null that was returned because that was actually the item in that position in the deck. Here, we're going through and throwing an exception instead when our deck is empty so that we don't have any worries about if we can distinguish things properly. When we go to peek at the front, we have the front index field that specifically tells us which array index contains the front of our deck. So here it's 3, and remember that arrays start off at 0, so we have 0, 1, 2, 3. Our value's A, and that's what we're going to go ahead and return from peeking at the front. The process for peeking at the rear of the deck is going to be fairly similar. We're going to start off by making sure that there are items in our deck, and if not, we'll throw that no such element exception. The one difference is that here I don't immediately know what the rear index is for my deck. We're not keeping track of that. But I can go and figure out what the rear index is since I know what the front index is and the size of my deck. So I'll go ahead and call the calculate rear index method, and that'll go and take the size and front index and pass those along to calculate array index to go and find what the correct position is for our rear index. Here, that's going to end up being element 1, where we have the C stored. Once we have that rear index, we can go ahead and return the value from our actual rear element. In addition to the peek front and peek rear methods that are required by the interface, we're going to create another method for peeking, and this one's going to allow us to specify the index of the item relative to the front of the deck that we're looking for. This is actually the one that's going to do pretty much all the real work of going and retrieving that item. This method I'm going to make be protected, and it'll have a T-type return value because we're going to return the value from that particular position in the deck. I'm going to call this peek element. And it's going to take an int that I'm going to call deck index, so the index relative to the front of the deck. Inside of this method, I'm going to start off by going and checking for an empty deck. So I'm going to say if this dot is empty, then I'm going to throw a new no such element exception with the message that my deck is empty. And I need to go and import the no such element exception class, so I'll use the quick fix in Eclipse to take care of that. I'm also going to go and handle the case here where the deck index that was provided was not valid. So if the deck index is less than 0, because we can't have negative indexes, or if it is greater than or equal to the size of my deck, and I'm assuming here that we've got 0 based indexing, then I'm going to go and throw a new exception. For this one, I'm actually going to use the index out of bounds exception type with the message that this was an invalid index for the deck. In this case here, I'm using index out of bounds exception rather than no such element exception, just because I think it's a little bit more descriptive of what's going on, and it also allows me to help differentiate between these two different situations, where the deck is empty versus where I had an invalid index. So that's why I'm choosing to go and throw this different type of exception here, although there's a reasonable case to be made for going and throwing no such element exception in this case too. But this is the design choice I've made. Once we get past these checks, what we're going to do is figure out which element we need to go and access from the data array. And for that, we're going to go and make use of the calculate array index method. We're going to store the value that gets returned as data index. I'm going to set that equal to this dot calculate array index. And my starting point for the first argument is going to be this dot front index, and then my second argument for the offset is going to be the deck index. So this is going to tell me which element from the data array actually goes and contains the value that is in whatever position I'm specifying here relative to the front. To go and get the value from that, all I have to do is just go to return this dot data sub data index. So we're just going to go directly to that element in the array and return its value. And we'll go ahead and provide some Javadoc for this method here. We're going to retrieve data stored at specified deck index. Our deck index is going to be the deck index relative to front of deck. And we're going to return stored data. I want to note both of the exception types here that we might throw. So we're going to say that we'll throw no such element exception, and that's thrown if deck is empty. And then we'll also have a throws tag here to go and say that we're going to throw index out of bounds exception when the deck index is invalid. Now let's go ahead and take a look at our peek front method. This method is really going to rely on our new peek element helper method to do all of its work. What we're going to do here is we're going to go and peek at the front element, and we're going to do that by calling this .peek element with a deck index of 0, because we're moving 0 positions over from the front since we actually want the front. We can just return the value from this. But there's something that we do want to think about here, and that has to deal with exception types. So we know that peek element will throw a no such element exception if the deck is empty, and it's going to throw an index out of bounds exception if the deck index is invalid. When we go and look at the Javadoc that we specified for deck interface, though, we don't have anything mentioned here about index out of bounds exception. We just have that we go and throw a no such element exception if there's nothing in the deck. So that kind of leaves us with a question of what do we actually want to do if peek element goes and throws an index out of bounds exception. If peek element goes and throws no such element exception, I'm just going to let that bubble up. I'm not even bothering to catch that one because that's an exception type that is documented that peek front might go and throw. I'm a little leery about going and potentially throwing index out of bounds exception as a result from a call to peek front, though, since it's not documented in the Javadoc. Now, I could go through and add that specifically to the Javadoc here for peek front, inside of my circular array Deque class, so that I would know that, okay, if I go and call this particular version of peak front, it might additionally throw this type of exception. But then I'm going to have a little bit of a mismatch between the interface documentation and the class documentation. And a lot of times people are just going to be looking at the interface documentation, so they might not even see that that might be thrown from the class. If we also kind of think about the behavior here, index out of bounds exception is only something that should be thrown if we have an invalid index, and we shouldn't really get an invalid index. Really, the only case that this should essentially ever come up here is if we've botched something someplace in our code. And if we've done that, it might just be because it really is empty and we didn't catch something right with our isEmpty. What I'm driving at here is that I'm actually going to go and set up my peak front method to go and catch the index out of bounds exception in the event that it were to be thrown. So for this, I'm going to go and create a try catch block, and my call to peak element is going to go inside that try catch block. So I put the try part here, and I'm going to say that I'm going to catch an index out of bounds exception, and then I'm going to stick it in the variable e. So now I've got a little bit more thinking here. What do I want to do? I've gone and caught this exception, and I could just sort of do nothing, but then I've got the problem of what do I go and return? Am I back to going through and returning null? I don't really like that solution. That was part of the reason why we were going through and throwing the exception for no such element exception in the first place here. The solution that I'm going to go with here is that I'm actually going to catch index out of bounds exception, which I'm doing right now, but I'm going to go and throw a no such element exception. That one is specified in the Java doc to say that the Deque is empty. Our situation may not be entirely that the Deque is empty, but at least it's something that we've got a problem with the items in the Deque. And I think that's going to be relatively helpful to users. So what I'm going to do here inside the catch block is I'm going to say that I'm going to throw a new no such element exception with the message that the Deque does not contain the requested item. And that does fit with kind of the meaning of what no such element exception is, even if I didn't go and explicitly document this scenario inside the Java doc. It's kind of a case of there's not really a great way to handle this. I'm kind of just trying to feel through which option logically seems to make the most sense, and I think this option here does. So that's what we're going to go with. Our peak rear method is going to be pretty much the mirror image of peak front. What we're going to do here is we'll set up a try catch block, and inside we're going to go and try to peek at the rear element and then return the value from calling the peak element method. Here I want to return this dot peak element, and for the Deque index to look up, I'm going to do this dot size -1. That's going to give me the zero based index for the rear item in my Deque. We'll go ahead and say that we want to catch an index out of bounds exception and stick in the variable e like we did above. And if we do happen to go and catch that exception, we're going to replace it with a new no such element exception, just like we did with peak front. So we'll say that the message here is that the Deque does not contain the requested item. Continuing on, we're going to have another pair of helper methods that are going to help us manage the size of our array. Since we have an array to store our data, we have the limitation that we can run out of space with it. So we want to have methods to allow us to grow and shrink the size of that array by going and actually replacing it with a new array that has more elements if we're trying to grow the size, or fewer elements if we're trying to shrink it. We're going to go and create separate methods, one to check for if we need to expand or grow, another to check if we're going to try to shrink, and that's to avoid inadvertently going and shrinking or growing things as we're going and making changes to add or remove stuff. We really only want to check to see if we need to grow at the time we go and add new items to the deck, and we only really want to check to see if we need to shrink at the time we go and remove items from the deck. We're going to take a look at going and growing things first, and what we're going to say for our criteria here is that if we have run out of space, then we're going to go and expand our array. So if there is any empty space remaining, we're not going to bother with expanding. We're just going to defer until we absolutely have to do it. In this case here, you can see on the screen, we have an array that has 4 elements in it, and we're actually using all 4 elements. Our size is 4. So we're going to have to expand the array. What we're going to do here is we're going to create a new array that's 50% larger. So if we had 4 elements before, we're going to have 6 with our new array. Where things are going to be a little bit different compared to the sort of resizing approach that we used with a traditional array is how we're going to handle the circular aspect of our array, where things go and wrap around. Because you can see in this example here, the front is actually index 3. It's this A that's at the end. If I all of a sudden have more elements, then it's going to be kind of messy if I try to keep things still wrapped around. So what's going to be a little bit easier for me to go and do here is I'm going to set the new array so that index 0 is going to be the front. So we're just going to kind of reset that array so that we start off with the front of whatever we have. If we go and start adding more items at the front, then we'll end up wrapping around again. But this way, at least as we get started, everything will be beginning at element 0. It's going to be a little bit easier for us to go and set things up because then I don't have to do any weird calculations about where to place the front. I'm just going to place it in element 0. So I'm going to go and essentially use peak element to figure out what value should be for each of these items, and I'm just going to go and copy them into the new array. So like here, if I do peak element with an index of 0, I get A. So I'm going to stick that in my new array's element 0. If I do peak element with a value of 1, I get B. So that's going to go in the new array's element 1. And then you can see I finish going and populating the array. In this case, I'm going to have some spare spots that won't be used, so those will just remain with null values. Since we've gone and repositioned things to make the front of our new array be in element 0, we're going to go ahead and set front index back to 0. And then we just need to go and store that new larger array inside of our data field. And that'll take care of going and expanding our array. Let's see how we actually want to code this up in Eclipse. Let's go ahead and make our new expand data capacity helper method. This is going to be a protected method, and it'll return void. And I said that I want to call it expand data capacity. I don't need to go and pass any parameters to it. What we're going to do inside the method here is figure out if we actually need to go about resizing things. So I'm going to say if this.size is greater than or equal to this.data.length, then we're going to have to resize stuff. What we'll do is we're going to make a new array that is 50% larger than what we have right now. I'll create a var called new data that's going to store our new array. The new array, for actually creating it, I'm going to make a new object. And I'm using object here because I can't create an array of a generic type. And inside the square brackets for the size, what I'm going to do is go and take this.data.length times 1.5. But I want to make sure that I end up with a whole number. And I'm going to have this go and round up. So I'm going to take the math.ceil to calculate the ceiling, or the integer that is greater than or equal to the value inside the parentheses. And since ceil goes and returns a double, I'm going to have to go and cast that to an int so that I can actually provide an int for the number of elements I want to have. Now I want to go and cast this new array that I've made to be my generic type. Can't create it directly as a generic type, but I can cast it to that. So I'm going to cast it as a T array, and then I'm going to go and use the quick fix here to go and add a suppress warnings for unchecked. And I'm just going to go and tag it for the method, although actually I can also go and do it just specifically for this particular new variable here if I want to be a little bit more limited in the scope of where I'm going and suppressing warnings. Once we have our new array made, we're going to go and loop to go and place the data into that new array. So this is a little bit more involved than just calling arrays.copyOf like I could if I was trying to resize a traditional non-circular array implementation. For my loop, I'm going to use a for loop here, and I'm going to create my counter variable I and initialize it to 0, and I'm going to loop while I is less than this.size, which is the number of things that I have stored in my deck, and each time through I'll increment I. And what I'm going to do inside the loop here is I'm going to set new data element I equal to what I get from going and calling peak element and telling it that I want to look at the value of deck index I. So this is going to go through, grab the values one by one starting at the front and place them into the new array, and we'll start actually placing things in element 0 like we talked about. Since the front is going to be element 0 when we're all done here, we're going to go and update our front index field. So we'll say this dot front index equals 0, and then I'm going to go and store that new array in place of the old one. So I'll say this dot data equals new data, and then I'm just going to provide a little bit of JavaDoc as this expands the data array as needed. We're also going to have a method that'll take care of shrinking the size of our data array if we find that we have a lot of unused space. Our criteria for triggering the shrink process will be if we're using less than half of the available elements. And what we actually do here is going to be pretty much the same as when we went to go and expand the array. Just the difference is that here we're going to have a new array that'll be 2/3 the size of the previous one instead of being 50% larger. With our smaller array, we're still going to go and copy over the values so that the front of the deck is going to go in element 0. Again, that just goes and simplifies us figuring out where we need to position stuff. Once I've gone and populated the new array, I'm going to set front index to be 0 to reflect that everything has been moved and reset with its position. And then I'm going to go and store that new smaller array in the data field to replace the previous larger one. I'm going to call my method here shrink data capacity, and it's also going to be a protected void method, and it will not require any parameters. We'll figure out if we need to resize the array, and the code's going to be just about the same as what we had up for expand capacity. Here we're going to see if this dot size is less than 0.5 times this dot data length. And if so, we'll go ahead and make a new array that is 2/3 the previous size. So I'm going to do this var new data, and it's going to be equal to what I get when I go and cast to a T array a new object array. And for the size for this new one here, we'll do the cast to int inside. We'll go and call math.ceil to get the ceiling of this .data.length, and I'm just going to multiply by 0.667, which is my close enough approximation for 2/3. And I'm going to go and add the suppress warnings to the method as well, so I don't have an issue with that cast. We're going to go ahead and loop to put things into our new array. So we'll do a for loop again. I equals 0 while I is less than this dot size. We're going to go ahead and increment I, and we'll set new data sub I equals this dot peak element with looking up deck index I. And then we need to go and reset the front to element 0. So this dot front index equals 0, and then we're going to use that new data array. So we'll say this.data equals new data. And just to wrap up, we'll provide some Java doc that this shrinks the data array as needed. Now that we have all of that prep work out of the way, we're ready to look at how we can go and add things to the deck. The steps that are going to be involved will depend on if the deck is empty at the start, and if it's not empty, if we're trying to add at the front or the rear of the deck. Let's start off by looking at the case where the deck is empty. This is going to be our simplest scenario. Here, we're going to make sure that the data array is large enough for an additional item, which it normally should be. And we're going to go and set front index to be 0. So if we have an empty deck, we're always going to place the very first thing that we go and add in element 0. And that's just sort of a convenience thing for us. It makes it nice if we go and try to debug what's happening with our code. We could do it without this, but it's a nice little thing to go and build in. So we're going to do that. We're going to go ahead and then store our new item in element 0 of our data array. And then we're going to increment the size field to reflect that we now have one thing inside of our deck. Let's say that we already have some things in our deck and we want to go and add our new item to the front. So it's going to come before whatever we already have in the deck. Right now we just have in our example here one thing in the deck, and that's in element 0, because when we first go and add something to the deck, it is always going to go in element 0. Here we'll start off by making sure that we have a large enough data array, which that's not an issue here. I'm going to go and update front index to be the element before the existing front. And here I'm going to keep in mind that my array is circular and wraps back around. So the element before element 0 actually turns out to be the last element of the array, which is number 3. So I'm going to set front index to be 3 to reflect that that is going to be the new front of our deck. Once I have that done, I'm going to go and store my new item in that element that front index now goes and points at. So A is actually going to go into element 3 here. And then I'm going to go and increment my size field to show that I now have two things. So we're going to start here with A in element 3. That's the front of our deck. And then we'll loop back around for our second item, which is going to be B from element 0. How do things work when we want to go and add to the rear of a deck that already has items in it? Here with this example, we have 2 items in our deck, and our front index is A. So the rear is going to be B, and we want to add after the rear, so we're going to go and add something after B. Again, we're going to start off here to make sure that we have a large enough array. We do, since we have some empty spots. What we're going to do is we're going to go and calculate our new rear index as being the element after the existing rear. So here, our rear is an element 0. So if I go and add 1 to that, my new rear index is going to be element 1. It's possible that I could have this go and wrap around back to the front. Just depends on how my data is actually laid out. In this case here, though, our rear is not going and wrapping back around. I'm going to go and store the new item that I want in the element with the index from new rear index. So our new rear here is going to be index 1. That's where we went and put the value C. And then I'm going to increment the size field to reflect that we have 3 things. So our front is actually starting in index 3 with A. We're going to loop around, have B and C, C being the rear, and then we have this one unused element here in between. So if I go and add to the front, my new item is going to go here. If I were to go and add to the rear, the new item would go there as well. Kind of the main difference in the outcome would just be whether my front index is going to remain at 3 if I were to go and add the rear, or if I go and add the front, then my front index would actually move up 1 spot to become 2. Let's go see how we can code things up in Eclipse. Let's go ahead and write the add to front method first, and this method will take care of if we're adding to an empty deck or one that already has items. our logic inside will handle either of those scenarios. We're going to start off with checking to make sure that we have enough room in our data array. So we're going to manage data array size by calling this .expand data capacity. Once I've done that, I need to figure out if I'm looking at a case where I'm inserting into a deck that already has values or one that's empty. And as part of this, we're actually going to go and determine what our front index should be. So I'm going to go and check to see if our deck is empty. And if it is, I'm going to hard code the front index to be 0. Just because, like I said, for debugging purposes and just kind of personal preference, I think it's easiest if we go and start off with the front in 0 if we're able to. So we're going to say nothing is in the deck. So we're going to start at element 0. So regardless of what front index is at this point in time, since we have basically a blank slate with nothing in the deck, we're just going to go and set front index to be 0. If there are already things in the deck, then I don't have that ability to go and arbitrarily say that our front index is going to be 0. We're going to have to go and calculate what the new front index should be. And it's going to be 1 before the current front. So here I'll say this .front index equals what I get back from calling the calculate array index method. And for the starting point, I'm going to pass the existing front index. And for the offset, since I want to go in front by 1 spot, I'm going to pass -1. So no matter which path we took, we're going to end up with the front index field containing where we need to be going and adding this new item to the deck. So we're going to place our new item in new front index element. Here we'll say this .data sub this .front index equals item. So we're going to go ahead and store that value that we're adding in our new location in the array. And then we're going to go ahead and update size. So we'll say this .size ++. So this will work if we have stuff already in the deck or not. I can call add to front, and it's going to go and get it in the right spot. Add to rear is going to be sort of similar. There'll be some minor differences when we figure out what location we want to go and add the new item. As with add to front, I can call add to rear whether or not I have an empty deck or one that has items in it. It'll go and handle both situations correctly. We're going to start off by making a bigger array if we need one. So we'll call this .expand data capacity. And then I want to determine what my new rear index should be. And I'm going to go and create a variable here that I'm going to call new rear index and make it be an int. And I'm declaring it right here just so that I don't have any variable scope issues, because I'm going to set this inside of an if-else block. My if-else block here is going to be depending on whether or not my deck is empty. If it is empty, we're going to go ahead and set front index to be 0. So we'll say this .front index equals 0. And I'm also going to make new rear index be 0, because if I'm only going to have one thing, it's both the front and the rear. So we'll say here new rear index is equal to 0. The else clause is going to handle where we already have things stored. And for this, we need to figure out where the new rear index is going to be. We're not going to change the front if there's already stuff stored in the deck. And so our new index is going to be one element after the existing rear. So I'm going to say new rear index equals what I get back from calling this .calculate array index. And for the starting point, I'm going to take what my current rear index is. I'm going to get that by going and calling calculate rear index. So that's going to be the first argument that I'll pass to calculate array index is where the rear is right now. And then my offset's going to be 1, +1, because I want to go one element afterwards. Once I've gone and worked out where we need to go and add the new item, we want to go and stick it there. So we'll say this.data sub new rear index is going to be equal to item. And then we need to go and update our size. So we'll have this.size plus plus. Now that we've added things to our deck, let's see how we can go about removing them. We're going to start looking at how we want to remove things from the front of the deck. So for this example here, you can see that we have a deck that has 3 items stored in it, and the front index is in element 3. What I'm going to do is take the value that's in the front of the deck, so that's actually element 3, the A, and I'm going to go and store it in a temporary variable. Once I've done that, I'm going to go and set that element where it had been to null. That'll reflect that the array element is no longer being used. I'm going to go and update front index to be the element that was after the old front. So here, where front index was 3, the next item in our array is going to be wrapping back around 0. So I'm setting front index to 0. Then I want to go and decrement my size field to reflect that I have fewer items stored. I'll shrink the data array if it's now too large. In this case we're not, because we're using exactly half the capacity. We only go and shrink if we're using less than half the capacity. And then once we've finished that up, if we need to go and replace the array, we'll go and return our removed value. So we're going to return that A value. Let's go ahead and code up our remove front method. We're going to start off by going and calling peek front. And this is going to do 2 things for us. It'll go and get us the value from the front of our deck, if there actually is a value there. And if there's not, it's going to throw a no such element exception. Peek front's not actually even the place where that exception is going to be thrown. It'll be thrown in peek element that peek front goes and calls, but since we're not catching it, it'll go and bubble on up. So what I'm going to do here in this line of code is I'm going to create my temp variable. I'm going to say var remove data. I'm going to set equal to this.peek front. Once I have the value that we're going to remove securely stored in that new removed data variable, I'm going to go to the array and set the element where it came from to be null. And that'll just reflect that we are no longer actively using that location in the array. So I'm going to say this.data sub this.front index is equal to null. Once I've updated that to null, I want to go and actually update what the front index is itself. So I'm going to say this.front index equals what I get back from calling calculate array index. And I want to go and set the starting point as this.front index, so the existing front, and my offset is going to be a positive number 1, so I go and find the element that's afterwards. So front index is now going to point at the new front. We'll go ahead and update our size by doing this.size minus minus, and then we can see if we should go and shrink our data array. Here we're going to call this .shrink data capacity. And then when we're all done, we're going to return the item that we removed from the front of deck. So we'll return removed data. Removing items from the rear of the deck is going to be sort of similar. Here with this example, we have a deck with 3 items where we're starting off at the front in index 3. And I want to go and store the value from the rear element, the one that we're going to be removing, inside of a temporary variable. So I've made this variable to keep track of C. I'll go ahead and set that element where we went and pulled C from to be null, since it's no longer in use. Then I can go and decrement the size field to reflect that we have 1 fewer item. We'll go ahead and shrink our data array if it's too large. And then we'll go and return the removed value. In this case, we're not adjusting the position of where the front is. We're removing from the rear. So I don't need to actually change front index inside of this method that we're going to be coding up. The remove rear method is going to be a slightly simplified version of remove front, basically because we don't have to go and update the front index. We'll start off by going and calling peek rear to go and get the value from the rear of the deck, assuming there was one, or to throw an exception if there wasn't. We'll go and store that value inside of a new variable called removed data. Once we have that value safely stored, we're going to go ahead and set the array element where it came from to null to reflect that it's no longer a valid value that we're storing. So I'm going to say this.data sub, and inside the square brackets, I'm going to go and call the calculate rear index method. And that's going to go and find the index where the rear, at least right now, is. So the thing that we're going through and getting rid of, and we're going to go ahead and set that to null. Then, once we've gone set to null, we can go and update the size by doing this.size minus minus. I want to make sure that I don't update the size until I have already gone and calculated the rear index. If I updated size first, I would actually get the wrong element to go and set to null. Once I've gone and updated my size, I want to go and shrink the array if we need to. So we'll say this.shrink data capacity, and then we're just going to go and return the item that we removed from the rear of the deck. So we'll go and return remove data. We're down to the home stretch here. Let's go ahead and fill out our size method. And this one's just going to be really simple. We'll return this.size. And we want to take a look at how we can go and iterate over the items that are stored in our deck. So for this, what we're going to do is we're going to loop, but we're going to start at the front of the deck. So we want to basically go and actually work through the deck in order relative to the front of the deck, not necessarily the order that things are actually stored in the array. So once we start at the front, we're just going to go ahead and loop and iterate over all the other elements until we get to a point where we've gone over all the elements that we're actively using, where we get to the element inside the deck that's size minus 1. We can go and use peek element to go and allow us to go and fetch these values, at least as they exist right now. Depending on what we're trying to do, we might be good with peek element, or it might be a case that, for example, we need to actually change values, in which case we would actually have to go and figure out which array index to modify. But if we're just trying to get the values as they store right now, peek element will do that for us. So that we can see how we might iterate over the contents of our deck, let's go ahead and complete the toArray method, which will create a new array that has each of the items that's stored in the deck in order. What we're going to do here is we're going to begin by going and creating a new array. I'm going to go and call it export array, and it's going to be a new array of objects size just large enough to fit the things that are in my deck. So it's going to be this.size for the number of elements I want to have. Then I want to go and get each of the items from the deck and go and store it in that array. I don't need to change the values that are stored in the deck, just get them. So peek element's going to work out great for this. We'll go and iterate over our deck items to populate the array. I'm going to do a for loop here. We'll say int I equals 0. While I is less than this.size, we'll go ahead and increment I. And I'm just going to say that export array sub I equals what I get from calling peek element for I. So this is kind of the same process we used when we were going and resizing the array internally to grow or shrink it. Once we've gone and populated the array, we can go and just return export array. With that, we're done implementing our circular array deck. For this lecture's participation project, I'd like you to start off by downloading the participation project starter code from eCampus. You'll need to import that project from the starter code into Eclipse. In Eclipse, I want you to go and create a new class that'll have a main method. And in that main method, you should go and instantiate the provided circular array deck class to create a deck that'll store integers. I want you to go and loop consecutively from 1 up to and including 50, and you should go and store even numbers at the front of the deck and odd numbers at the rear of the deck. Once you've loaded up the deck, I want you to go and iterate over it to remove items from the front and print each of those values one at a time until you've gone and removed everything from the deck. When you go to turn in your code, you should only submit the class that has your main method in it. That's where we're going to end things for our look at Deques for now. If you have any questions, join our Q&A session or send me an email. Thanks and have a great day.